All right, I wanted to give just a little context to some terminology that you've seen before in your previous algebra classes. So we're going to call x equals a, thinking of this as a vertical line, call x equals a vertical asymptote, which I'll abbreviate VA, for a function f of x, if at least one of the following three limits hold. Maybe more than one holds, but we're going to have the limit as x goes to a from the right or from the left. I'm going to say both of those at the same time to save a little writing. If either one of those limits is plus or minus infinity, or the limit as x goes to a in general of f of x is plus or minus infinity. And so if you think about it, that makes perfect sense. You guys have seen vertical asymptotes before. You've got a function. It's, whoops, that was a bad picture, but there's this vertical line and the function is shooting up to infinity, maybe on both sides, maybe just on one side and then going to the other side like that, whatever. But that's those lines we call vertical asymptotes, places where the function blows up to infinity. So you've seen that before, but now we have a little bit of calculus language behind it. Okay, so far we've been discussing limits of infinity, where the limit, the value of the limit, we're writing down infinity. When we say that, we know that the limit doesn't actually exist. There's not some number that the function is getting closer and closer and closer to, but something is happening. The function is getting larger and larger and larger. So now I want to switch our focus, and instead of talking about limits of infinity, I want to talk about limits at infinity. So I need a function that's defined on some open interval going from a point all the way out forever and ever, amen. So in this case, if I have a function that's defined on that interval, we say that the limit as x goes to infinity of f of x is the number L if the function f is getting closer and closer and closer to the y value L as x gets larger and larger and larger, as x gets arbitrarily large. And of course, there's a similar definition for the limit as x goes to minus infinity of f of x. And when we say that that is L, we mean that the function is getting closer and closer and closer to this y value as x gets large and negative. So somehow this should be relatively intuitive to you. You've seen these kinds of things before. But let's do an example just to make sure that we're clear. So I'm going to slide this up actually. So for this example, let's think about it together as you plug in big numbers. So maybe you plug in, let's think about f of x equals 1 over x. Let's name our function. And now let's start plugging in numbers. So f of 10 is 1 over 10. F of 100 is 1 over 100. F of 1,000 is 1 over 1,000. Please don't feel the need to compute these every time. I want you to see, though, that you can actually see as you plug bigger and bigger and bigger numbers in, the output, the y, is getting smaller and smaller and smaller. So this limit is 0. The limit as x goes to infinity. It just means x gets bigger and bigger and bigger. The function is getting closer and closer and closer to 0. We'll sometimes abbreviate this and we'll write it like this. We'll say 1 over x goes to 0 as x goes to infinity. You're welcome to use that notation. Well, that brings up another form that I want to highlight to you. It's not an indeterminate form. It's actually a form that you need to be aware of. So if the form is some constant c over plus or minus infinity, then the limit is 0. So that's a form you want to recognize. And by the way, it doesn't matter whether everything is negative. Negative numbers getting smaller and smaller are going to 0 just as well as positive numbers getting smaller and smaller and smaller. So let's end this video here, and we'll do some examples in the next video.